Your distributed database can only guarantee 2 out of 3 properties: consistency, availability, and partition tolerance. Pick 2. This is the CAP theorem, and every system design interview expects you to know it cold. Let me show you exactly how it works and how to use it. CAP theorem plus consistency models. High-level design, day 9. The CAP theorem, proved by Eric Brewer in 2000, states that a distributed system can provide at most 2 of 3 guarantees simultaneously. Consistency means every read receives the most recent write or an error. All nodes see the same data at the same time. If you write a value to one node, an immediate read from any other node returns that value. Availability means every request receives a non-error response, without the guarantee that it contains the most recent write. The system always responds, even if the data might be slightly stale. Partition tolerance means the system continues to operate despite network partitions. Messages between nodes can be lost or delayed. In any distributed system, network partitions will happen. Cables get cut, switches fail, data centers lose connectivity. This is not a theoretical concern, it is a certainty. Since partition tolerance is mandatory, the real choice is between consistency and availability. CP systems sacrifice availability during partitions. They reject requests rather than return potentially stale data. AP systems sacrifice consistency during partitions. They respond to every request but may return stale data. A CA system works only when there are no network partitions, which means a single node, not a distributed system. Let us look at CP versus AP in detail. CP systems prioritize consistency plus partition tolerance. During a network partition, CP systems reject writes to prevent inconsistency. Some requests return errors, but any data you do get back is guaranteed correct. MongoDB is CP by default. If the primary cannot reach a majority of replica set members, it steps down and stops accepting writes. HBase stops serving reads from regions that cannot confirm they have the latest data. Zookeeper requires a majority quorum for leader election and all operations. etcd uses raft consensus, which requires a majority to make progress. Use CP when correctness is critical. Financial transactions where a wrong balance means lost money. Inventory counts where overselling means fulfillment failures. Leader election where 2 leaders means data corruption. AP systems prioritize availability plus partition tolerance. During a network partition, AP systems accept all requests. They may return stale data. Conflicts are resolved later when the partition heals. Cassandra is AP by default. It is always writable because any node can accept writes. DynamoDB is available first, with tunable consistency per query. CouchDB supports multi-master replication with conflict merge. DNS returns cached records even when it cannot reach authoritative servers. Use AP when availability matters more than immediate consistency. Social media feeds where a stale post is acceptable for a few seconds. Shopping carts where losing an add to cart is worse than a brief inconsistency. User sessions where logging someone out incorrectly is worse than a stale session. There is a spectrum of consistency models from strongest to weakest. Linearizability is the strongest. The system behaves as if there is a single copy of the data. Every operation appears to take effect instantaneously at some point between its invocation and completion. This is what most people mean by strong consistency. The cost is high latency because every write must be confirmed by enough nodes before returning. Sequential consistency means all nodes see the same order of operations, but that order may not match real-time. If operation A completes before operation B starts, in linearizability, A must appear before B. In sequential consistency, B could appear before A. Less costly than linearizability, but still provides ordering guarantees. Causal consistency preserves the order of causally related operations. If operation A causes operation B, everyone sees A before B. But concurrent operations that are not causally related may be seen in different orders by different nodes. This is a good balance between correctness and performance. Eventual consistency is the weakest model. It only guarantees that if no new updates are made, all replicas will eventually converge to the same value. There is a window after a write where different replicas may return different values. This is the fastest option and what most AP systems provide by default. In practice, real systems are more nuanced than a simple CP or AP label. PostgreSQL as a single node is effectively CA. No partition tolerance needed because there is only one node, but this is not a distributed system. MongoDB is CP by default. If the primary cannot reach a majority, it rejects writes. But you can configure read preferences to allow stale reads from secondaries, moving it toward AP for reads. Cassandra is AP by default. Any node can accept writes. But you can use quorum consistency levels per query. With quorum reads and quorum writes, you get strong consistency for that specific operation. DynamoDB is AP by default, with eventually consistent reads. But it offers strongly consistent reads as an option per request, at higher latency and cost. The key insight is that real applications make different trade-offs for different operations within the same system. A banking application might use CP for balance checks and transfers, requiring linearizable reads and synchronous replication. But the same application uses AP for displaying recent transaction history, where eventual consistency is acceptable. An e-commerce platform uses CP for inventory counts to prevent overselling, but it uses AP for the product catalog, where showing a slightly stale price for a few seconds is fine. Design per operation, not per system. The CAP theorem only tells you what happens during a network partition. But partitions are rare. What about normal operation? The PACE-LC theorem proposed by Daniel Abadi extends CAP. If there is a partition, P, choose between availability, A, and consistency, C. Else, E, during normal operation, choose between latency, L, and consistency, C. PAC/ELC systems sacrifice consistency in both cases. Cassandra and DynamoDB prioritize availability during partitions and low latency during normal operation. Eventual consistency everywhere. PC/EC systems always choose consistency. MongoDB and HBase reject writes during partitions and accept higher latency during normal operation to ensure consistency. PA/EL systems are available during partitions and optimized for latency during normal operation. This is Cassandra's default configuration. PA/EC systems are available during partitions but choose consistency during normal operation. Cosmos DB with session consistency works this way. The key insight is that CAP only matters during failure. PACE-LC covers the normal case too. The everyday trade-off for most systems is latency versus consistency, not availability versus consistency. In interviews, mentioning PACE-LC shows you understand the complete picture, not just the simplified CAP version. Here is your CAP theorem interview framework. First, state the theorem correctly. In any distributed system, network partitions are inevitable. You must choose between consistency and availability during a partition, CP or AP. Second, never say CA distributed system. CA only works on a single node. If an interviewer suggests CA, politely explain that network partitions are a given in distributed systems. Third, acknowledge that real systems are nuanced. MongoDB is CP by default, but can be configured toward AP for reads. Cassandra is AP by default, but supports strong consistency per query with quorum. Fourth, mention PAC-LC for bonus points. Even without partitions, there is a latency versus consistency trade-off in normal operation. Common interview questions. Design a banking system. CP, because a wrong balance means money lost. Linearizable reads with synchronous replication. Design a social media feed. AP, because a stale post for a few seconds is acceptable. Eventual consistency with asynchronous replication. Design an e-commerce platform. Mixed approach. Inventory counts use CP to prevent overselling. Product catalog uses AP because a slightly stale description is fine. Design per operation, not per system. The best answers are not simply CP or AP. They show per operation trade-offs and explain why each operation needs its specific consistency level. 5 things to remember. The CAP theorem says a distributed system can guarantee only 2 of consistency, availability, and partition tolerance. Since partitions are inevitable, you choose CP or AP. CP systems like MongoDB reject writes during partitions to stay correct. AP systems like Cassandra accept all requests but may return stale data. There is no CA in truly distributed systems. Consistency exists on a spectrum from linearizability, the strongest, through sequential and causal, down to eventual consistency, the weakest. Stronger consistency means higher latency. PAC-LC extends CAP to cover normal operation. Even without partitions, you trade off between latency and consistency. This is the everyday design decision. And in interviews, design per operation, not per system. Stock counts need CP, product catalogs can use AP. Show this nuance and mention PAC-LC for depth.